We appreciate your time and your valuable time. Just a little bit about me. I know you're not here to hear about me, so I'll keep this brief. I'm the product manager at Larson Davis. I'm one of these oddballs that have worked at the same company pretty much my whole life and over 35 years here. And I also am a member of the IECT C29 committee for a number of years, representing the U.S. in the international standards for instrumentation. So that's just a brief bit of information about me. But what we're really here today to talk about is exposure, human exposure to vibration. So let's dive in here. I've got quite a bit of material to cover. I'll probably move pretty fast through it. If I skip over things or go too fast, please come back at the question and answer session and let's ask again so we can make sure that we get your questions answered. But just a few obvious things here to begin with, right? We all know that people are exposed to vibration routinely, and you can see a few photos here of that just to kind of give you an idea. And I have a few statements here. One here is from the U.S. Department of Defense. It's kind of a long one. I'll let you know I don't like putting a whole bunch of text on slides, so I don't think I have any that are worse than this one here. But you can see in here I've highlighted just a few of the key things in here. In the green, we can see that the HAVS, which stands for hand-arm vibration syndrome, which is the name given to what can happen from vibration exposure. It can cause loss of sensation, blood supply in the hand, and may cause loss of fingers in real severe cases. So in the U.S., it's estimated there's maybe 1.25 million people at risk of developing HAVS. I was also able to find something similar from the Canadian CREOD, the Center for Research, Expertise, and Occupational Disease. They estimated, and you can see I highlighted it there, that 10% of Canadian manual workers, which I interpret that as people working with their hands, could be exposed to significant HAVS risks. So the risk is out there, it's significant, and let's talk about it a little bit today so we can better understand it and what can be done about it. So just to kind of begin here, the exposure of people to, or human exposure to vibration is kind of divided into two big classes. The one we call whole body vibration, it's pretty self-explanatory, right? It's I'm sitting on something vibrating, I'm standing on something vibrating, my whole body shakes because of that. The other is hand-arm vibration, and again, excuse me, I think that's pretty self-explanatory too, right? It's typically associated with using hand tools, and most of the vibration is into a person's hand and arms. And they're treated quite differently in a lot of aspects, and we'll discuss that briefly as we go on. So let's just talk a little bit about who's at risk, and you can kind of see a few just examples of workers or jobs that could be at risk of hand-arm vibration syndrome or HAVS. And here's some pictures so you can kind of see what it's like. In the top picture that you see on the right there is milder symptoms. You can see kind of the darker fingers that happens. The photo at the bottom is an advanced serious case of HAVS where the fingers turn white, which is why sometimes this is also called white finger syndrome, kind of an obvious name that as it advances there. And so that's a disease that we're trying to avoid here. The technical name for this many times is Raynaud's phenomena or Raynaud's syndrome. And you can see here the quick list. A few of the symptoms and things that people would run into. You'll get cold fingers, you'll get tingling and numbness in the fingers, the white fingers we talked about, and it can lead to permanent damage. One thing about it, it's been found that this is exacerbated by cold weather. So it may mean up in Canada the risk is higher because you got some pretty cold weather in the winter time up there. And it seems that the cold affects the circulation with the vibration, and the two kind of work together to make the symptoms more extreme sometimes. So that's just a kind of a brief, quick introduction to what it is that we're looking at least for the hand-arm side. And whole body side, you know, we're looking for, you know, spine and nerve damage and things like that. But I want to shift gears slightly here and just talk briefly about what people have determined are reasonable limits for vibration to create a safe workplace where people are not harmed. So this little table here on the left are TLVs, threshold level values. For those of you not familiar with that, most of you probably are, and an action level. Those levels are ones that have been proposed by the ACGIH, or the American Council of Government Industrial Hygienists. Those also match the levels that are in force in Europe with EU directives throughout the EU. So we're a little different in North America. The Europeans kind of led the way in human exposure to vibration. They set up laws and requirements very much like what we have today for noise, they have for vibration. In North America, US and Canada, there are not specific laws and regulations, but the limits have been proposed by the ACGIH. There's also a page, you can see the link down at the bottom there to Ontario has also put out a page of information. What Ontario references is they reference the worker safety standard. It basically says, and there's a clause in there that basically says employers are to create a safe workplace, and that's what they're using right now as their reasoning for adopting these limits and proposing action on exposure to vibration. So you can see there for an 8-hour day, it's 5 meters per second squared is the vibration. Meters per second squared, for those of you not familiar with that, is an acceleration value, and that's typically, so it's an RMS, or if there's a pure scientist on here, they would get mad at me for calling it an average, because it's technically not an average, it's an energy average, but it's the average energy exposure for the day is 5 meters per second squared. And the limit value, the action value then would be 2.5 meters per second squared, or half that. The idea is very much like what happens in sound and noise. You should take measures to limit exposure to vibration in hand-arm to less than 5 meters per second squared. But if you're in that range between 5 and 2.5, then measures should be taken to allow users or workers to protect themselves on their choice. So that's a brief overview of limits and what it is. Let's talk a little bit about kind of a process that one would go through to determine, do I have a problem and do I need to take any action? So of course, first step is let's determine if I need to be concerned. You know, maybe I don't have a problem. And typically when you're going through this phase, you want to start out simple, right? And so here's some simple ideas that people can use to get started. So first one here is pretty obvious. Do you have power tools that are being used? And do you have a medical diagnosis of injury? If any of that's in place, you know, that's a really good sign that there's something going on there that maybe needs to be looked in further. A common symptom that's reported is the feeling of pins and needles in the fingers or something like that. Many of you have probably felt that yourself. I had an old blower, you know, that would blow, a leaf blower that vibrated like crazy, and after 15 minutes I'd get that pins and needles feeling in my fingers, right? That's that thing we're talking about. And the other one is obvious also. If you have a documented case of the HAVS syndrome, then that's a good clear indication that there's maybe something you need to look into. So after going through that initial assessment, if there's belief that maybe, you know, there's something I need to look into, the next step would then be to determine the exposure. And there's kind of two ways to do that. And we're going to go into a little more detail on these, but you can see that one would be to measure and the other would be to model. And I've got some slides to talk about that so you can kind of see a little bit more. Then, of course, last one, if after you've determined the exposure, you believe there's a risk, what are some things that can be done to mitigate that risk and provide a safe working environment for employees? So let's dive into those a little bit more. And here's a few more assessment questions that could be used when you're looking at what's happening in the workplace. And you can go down here and you can see this is basically, do I have people using things that are hand tools that produce a lot of vibration? Do I have warnings from suppliers? The other things that we've talked about, I'll give you a minute just to look down through the slides, but I won't read them to you because I know that's boring. So those are just some additional questions we can ask ourselves as we're evaluating our workplaces. So let's skip over now and assume that we've done our evaluation and we say, hey, you know, maybe I need to look into this further. Let's look into modeling first, modeling vibration exposure. So this is a way that has been proposed by a number of organizations to do it because it has some benefits, right? It allows a buyer up front to figure out, hey, if I'm buying something, what's the vibration of this? It's easy, it's relatively low cost. And so for those reasons, it's been promoted by a number of organizations, but it has some real challenges also. One is there's a lack of data. Another one is it's inaccurate. And by that, I don't mean that the data that you get from people is necessarily not good data or done correctly. But what I mean by inaccurate is the vibration exposure of a worker can vary significantly depending upon the work environment, the workers. So those things that can change the exposure of a worker, and I'll give you, at the very end here, I have some examples of that to show that to you. And the other is not representative of the actual conditions. And let me kind of explain that a little bit. There are international standards here, and you don't need to know these or memorize them. It's just to kind of give you an idea of what exists. But you can see there's ISO standards for how to measure the vibration of a number of different types of tools that vibrate. And these exist for manufacturers so that they can quantify the vibration produced by their tools and ideally label it. These standards apply, they try to make the data comparable. So these are drawings from the standard, but you can see the idea is that the measurements are made with a known force in a known direction, and so that as many conditions are kept the same except for the tool. That's great for getting data that you can compare one tool to another, but it doesn't help when you're trying to compare one worker to another or one use case to another case. And here I have a slide to kind of show what that would be. And let me explain this a little bit to you. So what you're seeing here in this slide is the light yellow bar represents the range of measurements that were made. So you can see the chainsaw went from maybe 1.5 meters per second squared all the way up to above 11 meters per second squared in a variety of measurements. So you can see there's large variability. The darker yellow or orange bar represents the range within which 80% of measurements occurred. So the orange is where a majority of measurements will occur. The yellow is the worst case to the best case. And so you can see there with these tools, the actual exposure of a worker can vary widely. And this is one of the challenges with modeling, is modeling will just tell you the average. And the average may be okay, but the actual exposure may not. All right, so continuing on with the modeling though, the way modeling works is you will take the predetermined vibration value of the tool and you can put it into a spreadsheet. This is an example of one produced by the health safety executive out of the UK. You can put that in there. You can see in that left column in white, you put the vibration magnitude. You can then put the exposure duration, or how long the worker is actually using that tool, in that white column to the right, and it will calculate an exposure for the day for that worker. Now, the interesting thing is there's two ways you can actually use a tool or a spreadsheet like this. One is you can put in the vibration magnitudes that are produced from some database or from the tool manufacturer, or the other is you can put in vibration magnitudes that you've actually measured. And both ways, can work. So let's step over and move into actually measuring vibration exposure. So the benefit of a measurement is it's more accurate, right? You get a measurement for the actual tool and the actual worker and the actual job that's going on. So you get more representative data of what's happening. And so you get an improved risk assessment, right? But there are challenges to that. It's more expensive. It requires specialized equipment. And sometimes measurements can be a challenge. And usually the challenge is you have a tool or something that it's not obvious how to measure or the vibration on that. And we'll talk just briefly about that and how to overcome some of those things. But before we go too far into the process of actually measuring, I want to lay a little groundwork here and talk first of all about something we call natural frequency. Sometimes you might have heard this called resonant frequency. And these are frequencies at which things naturally vibrate. So I put on here a picture of a guitar, right? You pluck a string and it'll naturally vibrate at a certain frequency, and that's how a guitar works. You blow in a flute, it vibrates at a certain frequency, and you get a tone out. That's natural frequency. Well, this phenomena also exists within the human body. So there are certain frequencies where hands and arms will vibrate naturally, or organs will vibrate naturally, and it's those frequencies where the natural vibration occurs is where damage also occurs, because the vibration gets amplified. Very much like the guitar string, right? I flick the guitar string, and it'll vibrate a lot more at one frequency than all the other frequencies. And that's important to be aware of when evaluating human vibration, and because we want to measure the frequencies where damage is most likely to occur and ignore those where damage is not likely to occur. So because of that, the standards group in cohorts with the medical community and the people researching this have created some weighting curves. And here's an example of what's known as the WH curve. So all these weighting curves have a W designation, and they have some letter after them. H is the weighting for hand-arm. And you can see this kind of, it might be a little hard for you to see, but it emphasizes frequencies around 10 hertz. And frequencies below that and above that are de-emphasized. So when making a measurement, you'll hear people talk about what weighting curve do you use, and that weighting curve is designed to measure the frequencies where the greatest risk occurs. And so the key thing to remember is WH is the weighting curve for hand-arm. It's easy, one curve, right? Now, if we move on to whole body, it gets a little more challenging because, when you look at the whole body, you have more resonant structures, and so different frequencies can have a different effect. So you can see here there's a whole bunch of weightings. There's a WB for Z-axis vertical. And if you look at this little guy here, you can see here, when we measure what's known as triaxial. So, the Z is the up and down, the Y is the side to side, and the X is the front to back, is what's meant to show here. So if I'm measuring in the Z-axis, my resonance structure would be my neck and my spine and those kinds of things. So I would have one weighting for that, like the WB, which is different, not could be, but actually is different than if I'm front to back or side to side. And so you can see over here we have different weightings for the different configurations. There was a question that came in the pre-questions about what about vibration in buildings. There's a weighting specifically for that, for comfort and annoyance, and that's called WM for vibration in buildings. So it gets a little more challenging in whole body because you have to match the weighting to the way you're measuring. Note that recumbent in the standards and in the speak of this industry just means you're laying down, right? So whether you're seated, standing, or laying down, there could be different weighting functions that apply. So with that said, I want to just give a little brief thing about standards because this can confuse people easily. So what happens is many times a person finds out they have a standard they have to comply with. Say maybe it's the one over here on the right, third one down, seats, ISO 10362. And they want to know, what do I need to do to measure it? Well, in the world of standards speak, they have what they call normative references. And a normative reference simply means that this standard is going to reference another standard, and that other standard should be considered as part of the requirement of this standard. So this chart is meant to show that here's an example of a bunch of standards, and they all reference these ISO 2631 standards for whole body measurements as normative references. Here's some, down at the bottom on the right-hand side are a bunch that reference the ISO 5349 for hand-arm. Both the whole body and hand-arm standards reference the ISO 8041 for instrumentation. So kind of the key thing from here is if you follow the chain back, it's quite consistent that instrumentation to measure whole body or hand arm should be compliant with the ISO 8041 standard. And that's how you can kind of figure that out, because if you're looking at the standard itself for maybe how to measure gloves, it won't say till you follow that chain back. And that's what can confuse people. So just remember, ISO 8041 compliance of instrumentation is the key for all these actual measurement standards. So let's take a quick look at just an example measurement system. This is the Larson Davis HVM 200 manufactured by us. It's a little device here you can see that fits on a person's arm or something. This silver device down here on the lower right-hand side is what we call an accelerometer. It looks like a little cube or a die or something like that, and it measures the acceleration. And then there's apps and software to gather the data. And that's a typical measurement system. And then we look at adapters and accessories. So you might remember earlier on I mentioned that, hey, there's some challenges in measuring, and sometimes that's how do I get a good measurement? Because the basic philosophy of human vibration measurement is you want to measure the vibration that the person experiences, which can be different than the vibration produced by the tool. And hopefully that makes sense, right? And so an example might be if I have a tool that's producing a lot of vibration, but the worker is holding it loosely, then they're not going to get all that vibration into their hand. Alternatively, if I have a tool that vibrates a lot, I think chainsaws are a good example of this. They vibrate a lot, but they have vibration isolation built into the handle, so the handle vibrates less than the tool. You wouldn't want to measure on the chainsaw. You want to measure where that vibration couples into the body to get a more accurate measurement. So what I'm showing in this picture here are a series of adapters that are defined by standards that are just used to help determine how to couple that or how to measure that vibration as it couples in. This one here that kind of in the middle here, that's called a palm adapter. That's typically used to measure underneath a glove, especially if you have a vibration isolation glove. You want to know the effect after the vibration isolation, right? This is called a handle adapter. The idea is the accelerometer mounts over here on this little V area, and the long part goes along the handle, so it can go out by the thumb or out by the pinky finger. This one we call the T adapter, and it's just meant to mount the accelerometer in the center part between fingers. And sometimes it's just not possible to mount in any of those places, and this is a clamp adapter. You can just clamp an accelerometer to a handle or something like that. So we'll talk a little bit about acceleration, just to give you an idea of what it is. Acceleration is the rate of change for speed or velocity, right? So we're pretty familiar with it. We drive in our car, we push the gas, we accelerate, we change our speed, right? Accelerometers simply measure that. And so it's pretty straightforward there. And just a little bit of information. So I had the slide earlier showing on the weightings for whole body, and we talked about the XYZ axis. And so this is common in the human vibration. You're going to measure vibration in XYZ. And this picture here of left-handed or right-handed coordinate system is a little tool that people sometimes use, right? You can take your finger, make an L, and stick the one finger out, and it'll show you kind of an example of the three axes. So what do we measure when we measure human vibration? We measure vibration in all three axes, and then we sum it up with this little formula you can see over here, which is a formula for RMS, and we report that sum. And that's what's done if we measure hand-arm vibration. And if we look at an instrument, you can see here you get a bunch of stuff. So ARMS is that sum of all the axes. So you can see that over here. Here's my RMS in the X, a Y, a Z, and I sum it all up, and that's the number I get. All right, that's the one we're interested in, really, is that one right there. And the industry also uses a metric they call A8. And this is simply the acceleration normalized to 8 hours, because just like sound, if I can trade exposure for time. And so an easy way to kind of deal with that is the A8 metric. We don't have time in this presentation to kind of go into the details of that, but we do have some information on that. If you're interested in learning more about the metrics, let Paul know and we can provide some information on that. There's a third key one known as vibration dose value, or VDV. This one's used in whole body measurement, and it is the sum of the fourth power, the sum of the fourth root of the fourth powers. It's used because it's been shown to produce a little bit higher number when you have impulsive type data. So an impulse, right, as I get a shock, I get hit. Those are known to be a little more damaging, and so this better represents the damage associated, or the risk, I should say, associated with impulsive type vibration. So that's just a quick introduction to some of the data and metrics that are measured. And the key ones like that ARMS are what you would put into that modeling spreadsheet. And as I mentioned earlier, just like in sound, you can trade exposure for time. Here's just a little chart of that. And that's important to note, especially when you're trying to mitigate the risk for workers. A little sample data here. This one here, the vibration levels were low in A8. So you can see here, and maybe I'll explain a little bit here, right? The RMS value was about 0.6 meters per second squared, which is well below the limit of 5 meters per second squared, so I don't need to worry. But the exposure time was low, So my A8 was even lower, and in this example here, there's no concern, right? No worry. So let's step on to then, okay, I've identified an area of concern, I've determined my exposure, and I believe that I have a risk. What can I do? And these are things you'll probably recognize them. They're very similar to what you would do with noise if you're involved with noise, right? First one is, if my vibration levels are high, let's lower them. And you can read there are a number of things that people can do to lower it. Sometimes it's just buy a newer tool. Sometimes it's train people. Sometimes it's just, use the tool less. And then here we're running out of time here, so I'll kind of move through this. But here's a couple of examples to just give you an idea of what we're talking about and see something in real life. This one here is a measurement of a forklift operator, and you can see here, if you look in the picture, there's a smooth concrete floor, then there's a floor made with small blocks. And if you look at the data, when this forklift operator, and you can also see there's a seat pad which is used to measure the vibration, whole body vibration when somebody's sitting on it, that's taped to the seat of this forklift. So the operator would sit on that pad and we'd measure the vibration that goes up through their buttocks into their body. So when they're on that smooth floor, we can see the vibration, or the ARMS, is approximately 0.31 meters per second squared, well within limits, right? Not a problem. But then if we look at the lower one there, when they're on the small block, the vibration is basically doubled at 0.63 meters per second squared. So it's the same tool, it's a forklift, the same operator, the only difference is where they drive it, and the vibration can vary by a factor of 2. Go the other way. Here's a hand-arm vibration tool usage. We'll talk a couple. One is just a breaker breaking rocks and, breaking small rocks. So here's the measurement of breaking large rocks with this breaker. You can see it's 24.4 meters per second squared, which is very, very high, much above the 5 meters per second squared limit. The small rocks is half that, or 12.6 meters per second squared. So again, same worker, same tool, just depending on, are they breaking big rocks? Are they breaking big rocks or small rocks? And that determines their exposure. And let's see, I'm going to move on here to a worker with experience and an inexperienced worker. So same tool, 2 different workers. Here's the worker with experience who over time has figured out how to minimize their vibration exposure and basically make their job easier. They get 4.2 meters per second squared. The inexperienced worker is 8.1 because they're probably fighting the tool more. All right. Well, everyone, I definitely appreciate your time here today and your attendance and the excellent questions. And I hope you found this of value.